So I think I would be remiss if I didn't include an example of a very popular computer simulation nowadays, which is simulate a pandemic. And the spread of a pandemic and how the number of people infected grows and falls. And we've seen how difficult that is, right? With the COVID-19 pandemic, we see that the predictions are very unreliable. Partially that's just because when you're dealing with human beings, then of course they react to the predictions that you make, right? So if you predict that the pandemic is going to be very bad, then people change their behavior, and then it won't spread as much, right? The people will practice social distancing and they'll wear masks. And if you predict that the pandemic won't be so bad, then actually maybe people will ease up and the pandemic could be worse than you thought. So there's all sorts of kind of perverse causality here. But I'm not going to attempt to do a realistic model of the pandemic, which, of course, is extremely complicated because you do have to take into account all of these social issues, like what fraction of people will practice social distancing, what fraction of people will wear masks, how often will they wear them, how well will they wear them. So all of these issues have to be taken into account. I'm just going to do a really simple model just to give you a taste for what's involved in doing this kind of simulation and what the complications are and what the pitfalls are in doing these simulations. So I'm going to simulate a small population of just 1,000 people. You can imagine that this is just the number of people maybe in one dormitory building, right, on campus. And I'm going to imagine that initially they're all healthy except for one infected person, and then we'll see what happens as one infected person potentially spreads the disease to others in this small community. What we'll do is we'll track the people according to what stage of the illness they're in, right? So, or another way to put it is we'll divide this population up into smaller cohorts. We'll have the healthy people who have never been infected and are susceptible to the disease, right? By the way, we're going to assume that nobody initially is immune. So the healthy people are healthy now, but they are all susceptible to it. So we will not assume that anyone has a prior immunity to this disease. Then another category, another cohort of the population will be people who are in whom the disease is latent, meaning they've been infected, but they are not yet either contagious or symptomatic, right? They don't know that they've caught the disease, and they're not spreading it yet. Next, the next stage of the illness is the infectious stage. Now, at this point, people are infectious. They can infect others, but they're still not symptomatic. So this is a very concerning stage of the illness because people can spread it without even being aware that they've contracted the disease themselves. Next, we have, I'm just going to call this the cohort of ill people, people who are symptomatic. They know that they've caught the disease. They're feeling ill. And I'm going to assume, and again, this is a very strong simplifying assumption I'm going to make here, that the ill people, as soon as they detect symptoms, they begin isolating themselves, so quarantining themselves, right? So that once they become ill, they actually will stay home and will stop spreading the illness. So in this simple model, I'm going to assume that the only stage of the illness at which people actually spread the disease to others is in the infectious stage. Okay. The final stage of the illness is when people have recovered and they now are immune. The whole question of immunity is also extremely complicated. There's some doubt about how long immunity lasts. Some people have demonstrably caught it more than once, although that so far the cases reported are quite rare. But it does seem possible that even if there is immunity, it may not last indefinitely. It might only last a couple of months. All of this is uncertain, but I'm going to assume that once people have caught it and recover, they are then immune. and they cannot catch it again. Okay? So, and then these 5 stages of the illness also correspond to the 5 cohorts of the population, and this is the order in which the people will cycle through the stages, right? First, they're healthy, then they become latent, and then infectious, and then ill, and then finally immune. And as I said, we will look at a dorm of 1,000 students, which starts with a single infection, just a single person who's infected, right? And we'll model it in time steps of 1 day, right? So each day we'll model the people interacting with one another, possibly some infectious person infects some healthy person, and the disease spreads. And each day, people may or may not go on to the next stage of the illness, depending on how much time they spend in each stage. And so on, and then we will simulate it 1 day at a time until finally everyone in the dorm is either healthy or immune. So in other words, there's no active infection in the community. Okay, so we have to make some assumptions about the numbers involved. I was kind of thinking about the COVID virus and what I know about it, but basically these are just invented. All of these numbers here are invented, and if you want to do a project like this, something about epidemiology, about the spread of an infectious disease, that would be very interesting to do. It would be a very good project. You should probably do some research into all the relevant numbers, right? And I'll mention some of them, and there may be others that you'd want to look at as well. So I'm going to assume that the latent period lasts an average of 2 days, right? So it's going to vary from person to person, but I'll assume that the average is 2 days. We can use, there are a number of probability distributions you could use that would be appropriate for this kind of thing. I'm going to use the exponential distribution, which is actually related to the Poisson distribution. It's actually the waiting time for the first event in a Poisson process. I'll say a little bit more about that later. The infectious period, I will assume, lasts an average of 3 days. The ill period, I will assume, lasts an average of 7 days. The ill period in this model will be the period when people are out of commission, right? When they're isolating, and therefore they're no longer having contacts with anyone, right? So they're temporarily reducing the size of the population. As I said, I'm going to assume that once someone becomes ill, that they immediately quarantine or self-isolate and will no longer infect anyone else. Again, that's an overly simplistic assumption, but it's not unreasonable for a simple model like this. I will also assume that each person has an average of 5 contacts with others each day, right? And that may be too low, it may be too high, I don't know, it depends on how strictly people are social distancing and or locking themselves down, right? This might vary quite a bit. That's something else that you might want to think about. I will also assume, and this is the one I'm most dubious about, I will assume that in any single contact between a contagious person and a healthy one, the probability that the healthy person becomes infected is 5%, 0.05. Right? That's really not based on very much of anything. I mean, I did a little bit of research, but that would be a very interesting thing to research and try to come up with a better or a good source for this number. This depends, of course, on a lot of things. It depends on the particular virus. COVID-19 apparently is particularly infectious. It's particularly easy to spread because it's spread through airborne particles, droplets. So that makes it particularly contagious. But then you also have to take into account, are people wearing masks? Are they social distancing? All that kind of thing. So I'm still counting a contact as a contact in which both people are wearing masks and they're remaining 6 feet apart. So that would lower the probability of infection spreading from the sick person to the healthy person, but it would not eliminate it, right? So you have to take all of those things into account when you come up with this number. So this is kind of an average probability of transmission from an infected person to a healthy person. From this number, right, from the assumption that the probability of transmission is 0.05, then we can also calculate the probability that if a person has contact with n contagious people, right, suppose a person comes into contact during one day with n contagious people, what is the probability that this person becomes infected? Well, the way to compute that, and this is what I tell my finite students, is to compute a probability like this, you want to use the complement method. We want to compute the probability that the person does not become infected, and then subtract that probability from 1 to get the probability that they do become infected. The probability that they do not become infected, well, in a single contact, the probability of not becoming infected is the complement of 0.05, which would be 0.95. In the course of n distinct, contacts with infected people, the probability of never becoming infected in any one of them would be 0.95 to the nth power, this guy. And therefore, the probability that you do become infected in at least one of those would be the complementary probability, so it would be 1 minus 0.95 to the n, right? So this is the formula we can use to model the event that a person becomes infected when they've had n contacts with contagious people. One thing that makes this simulation a little more complicated in a certain sense than the others we've looked at so far is that there are two levels to this simulation, two scales, you might say. There's the scale of the population as a whole. You're looking at the whole population of 1,000 people. But there's also going to be a simulation going on of individual people. In other words, for an individual person, we have to simulate them being healthy and then possibly becoming infected and then cycling through the different stages of the illness, from latent to infectious to ill to immune. And so we have to simulate the course of the illness in individuals, and then we have to keep track of each individual within the population as a whole. So in a sense, there are two simulations going on at different scales, right? For our purposes, the important scale is at the higher level, at the level of the population as a whole. That's really what we're interested in getting answers to about. Is what fraction of the population will become infected? How quickly will the infection run its course, right, to the point where no one is any longer going to be infected further? And how many people become sick? That kind of thing. Okay, so let's look at the attributes at each level. For an individual person, there are really only two things we have to keep track of. We want to keep track of what cohort of the population they're in, right? Are they healthy? Are they latent? Are they infectious? Are they ill? Or are they immune? And then one other thing is a number that tracks how much longer they will be in that stage of the illness or that cohort of the population. Remember, the person is going to spend a random amount of time, for example, in the latent cohort, right? We'll choose a random number at the beginning whose mean is 2, right? We said that a person spends an average of 2 days in the latent period. So we'll pick a random number to assign to the person for how long they will be in that stage, and then every day we will count that number down by 1, right? And when it gets to 0, then we know it's time to go on to the next stage, okay? So the two attributes will be which cohort they're in and how long they'll be in that cohort for until moving on to the next one. For the population as a whole, well, we're going to have a population attribute, which will be simply a list of all the individuals, right? So all of these persons with their attributes, they will all be in a list of everyone in the population. So we'll actually have a list of 1,000 people long, right, including everybody in the population. So this is going to be a large state because it'll have an entry for everyone in the population, all 1,000 people. And then these others are very simple. We'll just have numbers for the number of healthy people, the number of latent people, number infectious, number ill, number immune, and just to keep a running tally as we go along of how many are in each category. That incidentally will make it easy to see at the end when the infection has run its course. That will be when no one is either latent, infectious, or ill, when these numbers are all 0. Or alternatively, you could say when the healthy number plus the immune number is equal to 1,000, the total population will know the infection has run its course. Okay, so let's talk about how we update an individual. This is going to be somewhat complicated because we have to take into account both what happens to the duration, and then if the duration goes to 0, then that means we move to a different cohort. So I'm going to outsource this to a separate function. And what it has to do, so just to describe in words what it has to do, is it has to decrease the duration by 1. Right? The duration represents how long this person is going to spend in this particular cohort. So we decrease that by 1 each day. And normally that's all we have to do is decrease the duration by 1. But if that takes us to 0, so that the duration looks like it's going to be 0, that means we're actually at the end of that stage of the illness, and we have to move on to a new one. In that case, we have to choose a random duration for the new stage of the illness, right? And so what we'll do is we'll select a duration. If we're entering the latent stage, then we'll select a random duration using the exponential distribution. In other words, it'll be an exponential random variable. That's what RV stands for, random variable, with mean 2. And if we're entering the infectious stage, then we'll use an exponential random variable with mean 3. And if we're entering the ill stage, we'll use an exponential random variable with mean 7. If we're entering the immune stage, we're assuming that somebody's going to remain immune forever, so I will just enter infinity as the duration, right, that the person will remain in that stage. That's something Mathematica does understand. You can enter infinity as a number in Mathematica. Let me remind you, the exponential distribution represents the waiting time for the first event in a Poisson process, right? So you've got these random events happening at random moments in time, and then if you're waiting for the first event to happen, then the amount of time you wait is itself a random variable, and that is what the exponential distribution represents. It's called the exponential distribution because it turns out the formula for the density function, for the probability density function, it uses the exponential function. But the important thing is to know that it represents a waiting time, right? And that's kind of what all of these numbers are, right? They're waiting times until the current stage of the illness is over. So it seems appropriate to use the exponential distribution to model them. There are other distributions you can use. There's also something called the gamma distribution, which is closely related. It represents the waiting time until like the second or the third event in a Poisson process. And in some cases, those might be more appropriate, but we'll just keep things simple, so I'll just use the exponential distribution. And then we also occasionally have to update the cohort that the person belongs to. As I said, if a person has just come to the end of their time in one cohort, then they're starting on the next cohort, right? The next stage of the illness. One complication, though, is that if the person is healthy, we also have to consider the possibility that they may become infected due to a contact with someone who's contagious, right? And that's probably the most complicated part of the whole simulation. It's just modeling that. That's kind of the heart of the simulation, really. So we have to keep that in mind. In order to model that, one thing we need to know is a number which I'll denote as P, which is the fraction of the population that is contagious, right? So in order to know how likely someone is to become infected, we have to know what fraction of the population currently is infected, right? If there are more people currently infected, then there's more probability that you'll run into somebody who is contagious, and therefore more probability that you will contract the illness. So when we pass the task of updating the person to this update person function, we have to input not only the person we want to update, but we also have to pass along as input the probability that a randomly chosen person is contagious, right? So we'll do that using the variable P here. That's easy enough to get. We know the total population. We know we're going to be keeping track of how many people are in each cohort. The only cohort that is actually contagious and that actually has contact with other people is the people in the infectious group, right? The infectious cohort. And so everybody else is non-contagious or is just self-isolating, right? The ill people are self-isolating. So this number is very easy to calculate based on what we know about the size of the cohorts. Okay, and then at the larger scale, we have to update the main state, the state of the population as a whole. That's actually pretty straightforward. All we have to do is update every individual person in the population. So remember, the population is going to be a list of all the individuals in the community, and we just have to apply the person updater to each one of those persons, right? I'll just make a note that, as I said, it's easy to calculate the probability that a randomly chosen person is contagious, because the only cohort that is contagious is the infectious cohort, or rather, that's the only cohort that's both contagious and actively having contacts with other people. And the total number of people you might have contact with would be all the healthy plus all the latent plus all the infectious plus all the immune, right? Just leaving out only the ill people who we assume are self-isolating. And therefore the probability of encountering an infectious person or a contagious person is this number, right? So that's the value of P that we will input into the person updater, right? For every person. Having updated the population, then we just update the numbers, right? The tallies of all the healthy, latent, infectious, and ill. So we just count the number of each in the new version of the population attribute. Let's talk about this update person function. It has two inputs, the person to be updated and the number P, which is the probability a random person is contagious. This is the most complicated part of the whole simulation. I'm going to do it in two parts here. First, we'll talk about what happens if the person is in any cohort except healthy. In other words, if the person has contracted the illness, right? Then it's actually pretty straightforward, because what we do is we reduce the duration by 1, right? Because another day has passed, so we reduce the time they're going to spend in that stage of the illness by 1. And then if this new value is at least 1, that means they're going to remain in that cohort for another day. And then the only change that we make in the person is the duration. We just reduce that duration by 1, and the cohort remains the same. However, if the duration had been 1 and now we reduced it to 0, that actually means that this person has reached the end of their time in that stage of the illness, and so now we have to change the cohort, or change the stage of the illness, right? So we go to the next one in the sequence, and then we also want to initialize the duration, the amount of time they're going to spend in that new cohort. Once again, I'm going to outsource this. What I'll do is I'll define a separate function, makePerson, that takes one input, cohort. So this will just produce a new person, right, with those two attributes, the cohort and the duration, starting in the given cohort, right? We'll input the cohort that the person is supposed to start in, and then the make person function will assign the person to that cohort and also assign a random duration based on that cohort. Okay, so that'll actually be pretty simple to do. Okay, finally, the heart of the simulation. How do we model a healthy person possibly becoming infected? Right. So, in order to become infected, you have to have two unlucky things happen. You have to come into contact with an infected person, and you actually have to contract the infection. Right. Even if you come in contact with an infected person, you're still most likely, as we saw, we're assuming there's a 95% chance that even if you come in contact with an infected person, that you won't become infected, right? So I'm going to break this down into 3 steps. There's 3 random processes, or 3 random events that we have to look at. One is the number of people that you come in contact with, right? Remember, we're going to assume that each person has an average of 5 contacts per day. So what we can do is we can use a Poisson random variable with mean 5 to model the number of contacts that a person has on a given day. Right? So this n will be some random number whose mean is 5. Once we've determined what n is, right, then we know how many contacts the person has. But how many of those contacts will be contagious, right? Well, we have this number p that represents the probability that a randomly chosen person is contagious. So if you have n trials, so to speak, you have n contacts, and each contact has probability p of being contagious, then you can think of this as a series of Bernoulli trials, right? And you can think of this as a Bernoulli process, and therefore the probability that of a certain number of them being contagious is what's called a binomial random variable, right? So this is something that's studied, I'm sure, in 365, although I've never taught it. I know we teach it in finite math. We don't call it the binomial distribution. I think we just call it the Bernoulli distribution or the Bernoulli formula. But I'll use capital I to denote the number of the contacts who are actually contagious, right? People are actually infected and contagious. And this will be, we can generate this by using a binomial random variable where there are n trials, right, representing the number of people, and probability p of, I put success in quotes, because in this context, success means the person is contagious. Okay. Finally, if we know that you come in, or a person comes into contact with I people who are contagious, what's the probability that the person actually becomes infected? Well, we worked this out earlier. The probability of actually becoming infected is 1 minus 0.95 to the I power, right, where I is the number of contagious people you come in contact with. So finally, then, we just have to kind of flip a weighted coin, and the probability of becoming infected is this. The probability of not becoming infected is simply 0.95 to the I. So we flip that weighted coin to determine whether or not the person actually becomes infected. If they do become infected, then of course they will start out in the first stage of the illness, which is the latent stage. So we will just use the make person function that I mentioned on the previous slide and input latent, right, to create a new person in the latent stage with a new duration, right? Otherwise, if the person does not become infected, then the new person is exactly the same as the old, right? The new state is exactly the same as the old state. So now we can move on. Now that we've planned this in pretty fine detail, we should be able to move on and start coding this in Mathematica. Okay, let's talk about the Mathematica code. So on this first page here, well, of course, first of all, we want to load in the simulation pack as usual. But then I also have here, I have some just useful utility functions. That's kind of redundant, isn't it? A useful utility function. Utility functions to do some things that we'll need to do. So, for example, we'll need a random variable according to a Poisson distribution with a given mean mu. So this is a function that will simply return a random value from a Poisson distribution with mean mu. So Poisson distribution, this is a built-in function in Mathematica. And the input to this is whatever the mean should be, right? This is the mean number of events per unit time, right? So that's what mu is. And then, as I think I mentioned in an earlier video, that the random variate simply takes the distribution and produces a random value according to that distribution. Right? So the rand Poisson will just simply produce a random value according to the Poisson distribution with the desired mean. And then I'll do a similar thing to produce a random value according to an exponential distribution, again with a given mean. One thing I'd like to explain here is that I mentioned that the exponential distribution is the waiting time in a Poisson process. Now, a Poisson process, remember, has a mean number of events per unit time. That mean number of events is usually denoted by the lambda. Actually, over here I called it mu, but typically we use the Greek letter lambda to represent the mean number of events per unit time in a Poisson process, right? So if you think about it, if you've got, for example, an average of 3 events per hour in a Poisson process, then what's the average waiting time for the first event? Well, that would be 20 minutes, right? It'd be 1/3 of an hour. So if you have 3 events per unit time, then the waiting time is approximately 1/3 of a unit time. So if you have an exponential distribution with a particular mean, then the mean number of events will be the reciprocal of it, right? So the average of the waiting time is the reciprocal of the average number of events per unit time. So if we want a mean waiting time of mu, then we have to assume that the underlying Poisson process has an average number of events of 1/mu. And that is the parameter that you plug into the exponential distribution. It's actually lambda, the mean number of events per unit time. So that's why I wrote 1/mu here, right? Again, as a simple example, if we want to say the average waiting time is 3, then we should say that we want to think that the Poisson process have an average number of events of 1/3 of an event per day, and therefore the waiting time would be on average 3 days. Okay, so randx simply returns an exponential random variable with the desired mean. And then more specifically, I've got some parameters for this particular simulation. I'm going to denote the probability that an infection spreads from a contagious person to a healthy person. I'll call that infection prob, okay? I'll make that a variable. That'll just make it a little bit easier to tweak later. One thing you might want to do is see what happens if this number is bigger or smaller. How does that affect things? So it's just easier to change these numbers if you assign it to a variable, and then you only have to change the value once. You don't have to go back and hunt every time you use the number 0.05. You have to change it to something else. And then I have a simple random function for each one of the waiting times, right? So how much, what's the waiting time that somebody's going to remain in the latent stage? Well, we'll use the randexp function with a mean of 2, right? We want an exponential random variable with a mean of 2 to model that the waiting time or the duration that somebody will be in the latent stage of the illness. One thing here, notice that I'm applying the ceiling function to this, right? So the way the ceiling function works is it always rounds a number up to the next highest integer. So for example, the ceiling of 0.12 would be 1. You round up the number 0.12 to the next highest integer. I'm using that here because I don't really want any of the waiting times, any of the durations to be 0. That might actually make sense. That's something you might want to reconsider if you look at this for a project, you might want to reconsider this. But I just wanted to keep things simple, and it seems simplest to assume that people always spend at least one full day, in whatever stage of the illness they've just started on, right? If I allowed this to take the value 0, then that would mean essentially you could just pass through a stage and pass right through it and go to the next one. So I'm going to assume that that doesn't happen, right? So similarly, for the rand infect, this is going to be the random duration that somebody spends in the infectious state or stage. And again, I'm applying the ceiling function to the rand exponential function with mean 3. And rand ill, a random duration that somebody will spend in the ill stage, well, that'll be the exponential distribution with mean 7, and again, I apply the ceiling function to it to make sure it never, that it's a whole number. That's one thing the ceiling function does. It produces a whole number, and the other thing is this will make sure that it's never 0. Finally, random number of contacts. We're assuming that the number of contacts is an average of 5 per day, so I'm going to use the Poisson distribution with mean 5 to generate a random number of contacts for a given person on a given day. Let's look at the make person function. So this takes one input, which represents the starting stage for that person, right? The stage that person is just starting in. So this input could be, for example, latent or infectious or ill or immune or healthy for that matter. This is pretty simple. One thing that we have to do, though, is we have to choose the right duration depending on what the starting state is. So for that, I'm using a switch statement in Mathematica. So in a switch statement, you give it a particular value, and it sees which of the cases that value matches. So in this case, I'm going to give it the start value, which, as I said, it could be healthy or latent or infectious or ill or immune. And then we see, well, which value does start have? Well, if the value of start is healthy, then we'll say that the duration is infinity. As I said, infinity is a perfectly good number in Mathematica, kind of convenient sometimes. If the starting state is latent, then we use the rand latent function to generate a random number. If the starting state is infectious, we use the rand infect function to generate a random duration, and if it's ill, we use rand ill. If it's immune, then again we just set the duration to infinity. We assume the person will remain in that stage forever. And then finally, what we return is we return another association list, right? Remember, I always use these for the starting states. That's what's used in this simulation package. We always use these for the states. And so I'm going to use that to represent a person as well. A person will be represented by an association list like this, where there's a cohort attribute and a duration attribute. And in this case, of course, the cohort is set to whatever the input was, the start, right, the starting state or cohort, and the duration is set to this random variable t, which was determined by this switch statement, right, where we set a random duration depending on what the starting cohort was, right? So we return an association list with the given cohort and the given duration. I'm also going to use another convenience function that I didn't mention in the slides, but the next cohort function, just to tell me what the next cohort is. That's something that's easy to lose track of, so I just have a special function to tell me what the next cohort is after a given one, right? So the input is going to be one of these 5 cohorts. Well, actually not immune, because immune is the last one, but healthy, latent, infectious, or ill is the input. And again, I'm going to use a switch statement, right? So I'm going to switch on the input here, which was the given state, and then I say if the input state is healthy, then the next state is latent. If the input state is latent, then the next state is infectious, and if the input state is infectious, then the next state is ill, and if the input state is ill, then the next state is immune, right? So just so once and for all I can have a function that will just tell me what the next state is going to be without having to look it up each time. So now let's get into the update person function, right? The most complicated one. So remember, it takes two inputs. I'll use the variable per to be the person, right? Remember, the person is an association list with two attributes, the cohort and the duration. And p is just a number. P is the number that represents the probability a randomly chosen person is contagious, right? Random person from the population is contagious. Okay, first of all, I'll use a with statement here to define some local variables. So t will probably be the new duration. I'm just going to take the old duration, I'm going to subtract 1, right? So remember, person, I look up the duration, the duration attribute of the person, and I subtract 1, and that'll be t. And I'll also set co equal to the cohort of the person. So I'll take the person and I'll look up what cohort they're currently in, right? Now, remember I said things are relatively simple. If the cohort is not healthy, if the person is not in the healthy cohort, then there's only two things that can happen. If the simplest is if the time is still greater than 0, then the person still has more time to spend in that cohort. So then we simply return the value given by, we create a new person with the given cohort and the new duration, right? So the only thing we've changed here is we set the duration to t instead of what it was, right? We decrease the duration by 1. However, slightly more complicated situation, if t is equal to 0, right? So if t is not greater than 0, then we're in this situation. And then what we want to do is, well, first of all, we know we're going to move to the next cohort. So let's look up the next cohort. I'll use the next cohort function to look up what the next cohort is. And then we can simply make a new person who starts in that new cohort, right, in the next cohort. So actually, it's pretty straightforward. Because we already wrote the next cohort function and the make person function, this is actually quite simple. We look up the next cohort and we make a person in that new cohort. And that's the value that we would return. Okay, finally, we get to the heart of the simulation. What happens if the person was healthy? Then we have to simulate them meeting a random number of people. Some of those people may be contagious, and then you might possibly catch the illness from one of those people. So, first thing I'll do, if the person was healthy, then first I'll use a with statement to define a local variable equal to the number of contacts that the person has on this day, right? So I'm going to use the ran contacts function I defined earlier to just generate a random number whose mean is 5, right, to represent the number of contacts. Okay, now of those contacts, remember the variable p was the probability that a random contact actually isn't contagious. And so the number of people that you come in contact with who are actually contagious, I'll call that inf. So INF, and that's going to be have a binomial distribution. So I'll use a binomial distribution to generate a random number of infected people that you come in contact with. By the way, this function, ran binomial, this is not built into Mathematica, but it is built into the simulation pack, right? So we loaded it with the simulation pack. It simply produces a random number according to the binomial distribution, where the number of trials is the first input and the probability of success is the second input. So in our case, the number of trials is the number of contacts, and the probability one of those trials being a contagious person is p, right? So this will give us a random number of infected people. And then we want to compute, well, what's the probability, therefore, that this healthy person catches the illness? Well, I'm going to outsource that to another function, prob infection. So let me just talk about it. It's just a one-liner down here. So prob infection, the input is the number of infected people you come in contact with, and it simply applies that formula that we saw, right? So in our case, it's going to do 1 minus 1 minus 0.005 to the n, right? So this is going to be 1 minus 0.95 to the nth power, just like I talked about in the slides, right? Okay, so if we know the number of infected people, we can just call that function, input the number of infected people. This will give us the probability that our healthy person becomes infected. Finally, well, maybe not quite finally, but another built-in function built into the simulation pack is rand-bool, short for random Boolean. Remember, Booleans are things that are either true or false, right? The values are either true or false. So what this does, it returns true or false according to the probabilities that you input. So this is the way it works. You input a probability, and then rand-bool will be true with the probability that you input, and it will be false with the complementary probability. So basically, rand-bool is like flipping a coin and saying, heads comes up with the probability that you input, and tails comes up with the complementary probability. So prob is the probability that this person gets infected. So if rand-bool of prob is true, we're going to take that to mean that the person did in fact become infected. And in that case, we make a new person who's in the latent stage. If rand-bool of prob is false, we take that to mean that the person did not become infected, and then we just return the old person unchanged, right? The old healthy person unchanged. Okay, now, how do we make the starting states for this? I'm actually going to use a function that will produce a given starting state for a given population size. I said that we're going to do a simulation of 1,000 people, but we might want to vary the size of the population and see what effect that has. So I decided to make this a function rather than just a constant. So it's the make state function. The input is the total population size, right? So we'll run it with make state of 1,000. And then the initial state sets the time equal to 0. It sets the healthy population, the number of healthy people equal to the total population minus 1. It sets the number of people in the latent cohort to 1, and all the other cohorts to size 0. And then finally, it's going to generate a list of people, right? The population is supposed to be a list of all the people. So we have to make persons, right, for all of the people in the population. So what I do is I use the table function here to make a list of persons. Each person is going to be healthy, and the number of healthy people is going to be the population minus 1. So this statement produces a list of pop minus 1 people who are all in the healthy stage. Okay? To that list, we're going to append one extra person, the ill person. So we append to that list of healthy people one person who's in the latent stage, right? And at the beginning of the latent stage. And so that will be our starting population, right? In our case, it'll be 999 healthy people and one person in the latent cohort. So now we can talk about the updater. This is actually going to be quite simple. We've done all the hard parts. First of all, I'm going to define, again, a separate function, an update pop function that will update the population attribute, right? So in other words, the input here will be the population, the list of all the individuals, and number p, again, the probability that a random person is contagious. And this works very simply. There's a very simple way in Mathematica to apply a function to each entry in a list. The shorthand for this is you use this symbol. There's some weird symbols in Mathematica for the shorthand that they use. But this symbol, / symbol, it says apply the function on the left to every element in the list on the right. Okay? So this is going to apply this function on the left, which I'll explain in a second, to each individual in the population list. Okay? Now, this function on the left, and let me explain this. Now remember, we had an update person function that takes a particular person as the first input and a probability p, and then returns the updated person. Because in this case we want to apply this to different people, I've replaced the person, the first input, by a pound symbol. So that represents an input. That the input could be anything. And the ampersand at the end here means let's interpret this whole thing as now a function of the inputs, which are represented by the pound symbols. Okay, and one more time. This represents a function in which the input is a person, and the output will be the updated person, updated according to the probability p. Right? So we take this function, which you can apply to any person, and we apply it to each person in the population list, and that will give us the updated list. So that's how the update pop function works. It'll just update the entire list of the population. With that, it's very simple now to define the updater. It's going to be a list of these delayed rules. This is what they're called in Mathematica. The colon means delayed, and the arrow means it's a rule for replacing one thing by another. So we update the time by just increasing the old time by 1. We update the population by using the update population function, and we apply it to the previous population. And P is what I described in the slides. It's the number of infectious divided by the number of healthy plus the number of latent plus the number of infectious plus the number of immune. Right? That's the formula for P, the probability that a random person is contagious. And then this is pretty straightforward. I'm going to use the count val function that I've talked about before. We can count the number of states or objects with a certain attribute using the count val function. So we're going to update the number of healthy people by counting the number of people in the population whose cohort attribute is healthy. Right? So that's how this count val function works. Count the number of people in the population whose cohort attribute is healthy. And similarly, we'll update the number of latent people by counting the number of people in the population whose cohort attribute is latent, and so on. So we do the same thing for infectious and ill and immune. And that's the whole updater. It's actually pretty simple. So we're ready to actually run the simulation now. So our starting state will be a state produced by applying the make state function with an input of 1,000, right? So this will produce a population with 999 healthy people and 1 person in the latent state. We want to run it until a certain condition is satisfied. So I'm going to use the run till function from the simulation pack to run this. So we give it the starting state, the updater, and we also give it the condition it's looking for when the simulation should stop, right? It should stop running. So in this case, there's actually a couple different ways you could do it. Here I'm going to use, we run it until the number of latent people plus the number of infectious people plus the number of ill people is equal to 0, right? So there's nobody in any of those 3 categories. So that would imply, therefore, that everybody is either healthy or immune. So everybody is either healthy or completely recovered. And at that point, it's no longer possible for new people to become infected. At least internally. Of course, people can always become infected from external sources, right? Somebody travels outside the norm and maybe contracts it, but you can no longer contract it from internal sources. So you should run this and see what happens, to test it. I am not going to do that because it takes up a lot of space. Notice that each one of these states, right? Each one of these states at each step in the run is going to contain an entry for every one of the 1,000 people. So this is going to be a really long output, right? It's going to be, like each day is going to be like 500 lines long. So I'm not going to do that, but it is something you'd have to do to test it. So I'm going to skip over that now. Let's just go ahead and collect a bunch of data. I'll use the run till many statement, takes the same first 3 inputs, the starting state, the updater, and the condition for when the simulation should end. But in addition, the 4th input is how many times you want to run the simulation. So we'll run it 1,000 times, and we'll get data on 1,000 runs. Now, actually, I'm not going to run it right now. I ran it earlier. I'm not going to run it now because not only the output's big, but the simulation runs slowly because, again, it has to, for each day, it has to update each of 1,000 people every day, right? And so if you're going to run this, do 1,000 simulations, then, you're talking about updating a million, people over the course of the many days that the epidemic lasts. So that takes a while. Even in on a modern computer, it can take anywhere from 20 minutes to a couple hours to run, and depending on what exactly the settings you use when you set those variables, right? You set those means and things. Okay, I did run it earlier, and so I was able to check what's the mean number of immune people. What this tells us is the average number of people who contract the illness, right? Because if you contract the illness, then you eventually become immune. So at the end of the simulation, the number of people who are immune is the same as the number of people who caught the illness during the whole course of the simulation. And you see, in this case, it's not a large number. It's only about 7 people, right? So in this case, because the probability of spreading the illness from a contagious person to a healthy person was rather low, only 5%, that meant that typically an outbreak is only going to reach about 7 people. Right. Of course, that might vary depending on other considerations. It may be that if maybe people do not begin to quarantine as soon as they detect symptoms, right? It could be that they remain active in the community until maybe the 2nd or 3rd day of their illness. In which case, this number would probably be higher. Those are all things that you might want to test if you want to do a variation of this. Another thing that can influence this is exactly how strict people are about social distancing and mask wearing, right? All of those things might influence the probability of a contagious person infecting a healthy person and might raise or lower that number from the 0.05 that we've been assuming. And then finally, I also looked at the mean of the time in all the data. So remember, the data contains the final state of each simulation, of each of the 1,000 runs of the simulation. So the time in that last state tells us how many days the epidemic lasted until it petered out, right? So it turns out that the average length of time that the epidemic lasted was 26.5 days. Again, in this case. And again, that's something that could change drastically if you tweak a couple of those parameters that we used in this simulation. There are other things you might want to look at, which you might want to look at in all of these simulations. What was the most amount of people who ever became ill? Let's just consider that one. Let's take the data. And why don't I apply a function that just extracts the number of people immune. So I'll apply that, and let me set this equal to number immune. Okay, so what this does is it's going to set this variable number immune to actually a list. It's going to apply this function, which just takes an individual data point from the data list and looks up the immune attribute, right, the number of people immune. And let me put a semicolon because this is going to be a long list. It's going to have 1,000 numbers in it. Okay, so that's the immune list. And now let's just look at the mean of this. So there's a built-in Mathematica function for this, the mean of the number immune. And that actually should be the same as 7.105. Yeah, let me change that into a number. Yeah, 7.105. But another thing you might want to look at is the maximum. What's the max of the number immune? So in the worst case scenario, how many people caught the illness? Oh, So it could get as bad as 268 people out of 1,000 catching it, right? Even from one person. So that happened in at least one case in these 1,000 simulations, that the infection spread to 268 people, right? I would guess that the min of the number was probably 1. It's possible that one person who started with the infection might be the only one who ever had it. It might not have spread to anyone. Yeah, so the min number was 1. So you can see that in our 1,000 runs of the simulation, the number of people infected varied between 1 and 268. So there's quite a lot of randomness involved here, right? Whether the illness passes on depends on random events, who meets who, and what kind of interaction they have, and whether the virus happens to be transmitted or not. And there's a lot of randomness involved in this, right? So even though the mean number of people infected was only 7, in a bad case, it could be rather bad. You could get a quarter of the dorm infected, right? So this is something you could think about doing for your project, and I'm happy to talk to you about it and what kinds of variations you can and should do. You obviously should not do exactly the same simulation. You should try to look at what happens when you make slightly different assumptions. You might want to compare what happens under different assumptions about the parameters, or you might want to introduce new ideas to try to make the simulation more realistic under certain circumstances. But those are all things you can talk to me about.